see, I'll go first today. Today will be a split lecture day. Today we're going to talk about fission, about the phenomenology of it, a little bit of the history of it. The history is absolutely fascinating. And then Professor Knock will take over and we'll keep going with the history of the U.S. and Soviet nuclear weapons program and so forth. I have now put up on B courses the first 3 lectures, the PDFs, on what we've done so far. I've also put up the Los Alamos primer that Serber sort of indoctrinated the new troops that were dragooned from universities, grad students and recent graduates at Los Alamos in 1941, 42, 43. You can look at them, appreciate them, rub your hands on them, tell your grandchildren you actually touched the Los Alamos primer, the unclassified version. It says right up the front that it's been scrubbed appropriately, declassified. And also this article I told you about by one of Berkeley's own faculty members, Thomas Carlyle Smith, who was a professor of history, died in 2002, who taught, it was a personal memoir on his being a Japanese language translator in the occupation force in 1946. And he was the one, as he got to know Kyoto very well and university and the shrines and so forth, bopping around in an army jeep, he was the one that got the orders to escort these people from the Navy to the Kyoto cyclotron and to dismantle it and to dispose of it in the ocean. And it's a very touching, it was about a 5-6 page article on his experience and then coming back to the United States, going to graduate school and then becoming a historian. There, a very poignant little piece of personal history, kind of makes real the whole thing. Okay, we've mentioned before the nuclear fission in December of 1938. Fission had a little prehistory to this. The Fermi had been irradiating ore, the uranium and other actinides with neutrons in the mid-30s, and then doing some chemistry on them, seeing some things which are chemically different. Although they looked like the chemical properties of lighter elements, he said, well, this always happens in the periodic table. These various rows, things in a particular column kind of behave chemically like their lighter precursors. He assumed that he was actually making elements heavier than uranium. But it turns out he was deceived. I got a lot of credit for this. And then I think it was Nordach, who, a German chemist, believed that this was in fact a fissioning process, wrote a paper, but the paper did not get a lot of traction at the time. This was already in the mid-30s. By December of 1938, there were experiments done by some very eminent chemists, Hahn and Strassman, and assisted by Lisa Meitner, who was a physicist and a theorist, that began to make convincing that they were actually seeing real mid-weight elements after neutron bombardment of uranium. And you can see how this whole thing went, particularly physicists looking at chemists saying, oh, you know, they're doing chemistry, they irradiate us up with neutrons. You see trace amounts of these things here. Clearly, this was a contamination. You pay no attention to this. That was kind of a whole dynamic of why it took so long to establish the validity of this claim. But ultimately, they made the claim that they were seeing indeed lighter elements. So, and here are the players. There's Otto Hahn, Fritz Strassman, Lisa Meitner, and her nephew, Otto Frisch. Ultimately, what was established, they were able to clearly demonstrate that one very common pair of fragments that came out, fission fragments that came out from the splitting of uranium, was barium plus krypton. But they were seeing, in fact, a whole spectrum of lighter isotopes. And finally, they boldly, Strassman and Hahn, wrote up a paper individually that claimed that the atom was being split. This was very puzzling to theorists at the time, to physicists. They did not understand how a single large nucleus with a very slow neutron coming in could actually end up being two mid-wave fragments. And there were some quite fundamental things that they were overlooking. Meitner, this was all at the Kaiser Wilhelm Institute in Berlin. Meitner had Jewish ancestry and hung on to her job as long as she could. But finally, at some point, things were becoming problematic enough that she left rather hastily to Sweden. She went, in fact, to the Nobel Institute in Stockholm and worked there. And when she received news of this report, that her nephew, who was here, Otto Frisch, came and visited her and spent some time with her, and they began to ponder, what on earth does this thing mean? She was the one that kind of figured out the mechanism based on the liquid drop model of Weizsäcker, and Bohr was partially involved, that said, well, you know, the nucleus is really deforming and then breaking into two fragments, and then these fragments are chemically pushing apart from one another. By that time, people had actually done measurements in ionization chambers that showed that these signals of these recoiling nuclei were leaving massive amounts of energy in ionization. But she calculated these two fragments, once the fission happens, the neck breaks and the fission happens, that the Coulomb repulsion, when they actually separated enough, so effectively they're at sort of infinity from one another, would have kinetic energies of close to 200 MeV. So she actually hit it right on and everything fit rather nicely. There was an interesting story here. Apparently, Lisa and her nephew Otto went walking through the snowy woods on snowshoes, and they were talking physics all the time, and they went to a tree stump apparently and were drawing pictures with their fingers, and Meitner said, well, I think it looks like this. Fission looks like this. And he said, no, it looks like this. I think, he said, I think that's the wrong picture. He says, I think it really looks like this. And she said, well, that's what I drew. So he was simply thinking about visualizing it from the end on. But in fact, that was the picture that he had that in this Bohr Weizsäcker liquid drop model that that you can think of atomic nuclei. Then absent from the work that Strassman and Hahn were doing, I think she was a little bit out of the loop. They got most of the credit for fission, Nobel Prize, and so forth. But I think history has, done much, to kind of reinstate her to the proper position she has here.
Go
ahead.
So only recently, in the last few years, there was a movement. Strassman and Hahn had received the Nobel Prize. Meitner wasn't mentioned. Now, of course, she was a Jewish emigre in Sweden from Germany. But the Nobel Committee was pressured to distribute her papers to a variety of current physicists and make a judgment about how central were her ideas to what Hahn and Strassman did, and they said totally central. But for some reason they couldn't retroactively give her the Nobel Prize. And this was also an issue of, the woman didn't get the prize. It was a gender issue here as well. So she was really deserving. So her thinking was central to this, but she was never fully recognized for what she did. This was just a few years ago. There was a big argument about it.
Actually, let me reorder my slides since I'm on a roll talking about history, and then we'll go into a little bit more of the systematics here. I think it's more fun to do this thing in proper order. the Hungarian physicists. Fermi, if you like history of physics, there's actually a book out called The Martians of Science. There were a number of Hungarians that were all born within literally a few kilometers of one another, approximately at the same time in the Carpathian Mountains. This was Teller, there was Szilard, there was von Karman, aerodynamicist, there was Eugene Wigner, and there was a whole bunch of these things. And these guys were off the charts brilliant. And Fermi was so impressed with these guys that he joked, he said, actually, these are not men. They're Martians that came down in the likeness of men. But this is really a super race, and he actually called them the Martians of science. Szilard was an interesting guy because he wasn't kind of on the mainstream of physics. He was a guy who, he actually, I think, was self-described as being very lazy. He liked to take long, relaxing baths and think about things and be kind of a provocateur, make things happen. But he wasn't one of these guys doing kind of the hammer and tongs research on a day-to-day basis. Apparently, in the 1930s, long before, shortly after the neutron was emitted, but before fission was discovered, he actually said, imagine that there is that a nuclear reaction could produce two neutrons, and each neutron could induce another reaction in a nucleus that would create another two neutrons. You would get a chain reaction. Now, that's a little bit building castles in the sky if you do not understand that the actinide nuclei can fission, and these neutrons of energy can give you back your neutrons. But he actually had the idea of a chain reaction long before anybody discovered fission, which is quite interesting. He even had a patent on it. This is a photograph of him talking with Einstein. Not sure whether that was the actual discussion about Long Island to getting Einstein to write Roosevelt, but that's certainly what I think it would look like. Now, getting back to our topic here. This was December of 1938. Niels Bohr took a ship, which is the way most people traveled to the United States. He landed in New York Harbor on January 16th of 1939. He immediately told, and here the history gets cloudy, he claims that he told Fermi, who happened to be visiting Columbia at the time. Fermi later said, no, he told Robbie, Isidore Isaac Robbie, and Robbie told Fermi. But anyway, anybody was anybody very quickly began to pick up the buzz that fission had actually been unequivocally tested as and been proven as a process. News quickly got to the West Coast as well. Out here, Louis Alvarez, who was a student of Lawrence's, was actually trying to get people had been thinking that fission might happen under radiation neutrons, but they didn't quite know how to, that this was true or how to do the experiment. He was literally getting a haircut on Shattuck Avenue. One of his colleagues came in and said, did you hear the news? Fission's been discovered. Apparently, he gave the guy a couple of bucks, went running out of the barbershop with about half his head done, went up, and they immediately set up an ion chamber with a thin film of uranium up at the 60-inch cyclotron, and they said, my God, we have been idiots, we missed it. So things really moved very quickly. The really important thing happened here. This was now 1940. Two gentlemen, very important here. This Alfred Neer was a professor at Minnesota. And to the left there is John R. Dunning, who was a professor at Columbia University. Dunning had, this again before big science, took some spare parts and scraped up some money and built the cyclotron at Columbia. There weren't so many in the world at that time. There was, just a handful of, there was the 60-inch cyclotron out here. Lawrence would then build a 184-inch cyclotron under that big dome you see on the hill that now has the advanced light source. And here is on top Alfred Neer, who was a very famous guy because he at that time really perfected or developed high resolution mass spectrometers. And I'm forgetting who it was now, but sometime in the mid-30s, somebody had figured out that there were two stable isotopes, or quasi-stable isotopes of uranium, one of them being 235 and one of them being 238. 235 is a minority species. It's a very tiny fraction, 0.72%. So 1 part in 140 of natural uranium is 235. 99.3% is uranium-238. The question is, which of them was fissionable under slow neutron bombardment? So here is NIRS spectrometer. I love what these guys did, and this was, old-fashioned physics. It's a work of art. Simply, glass blower, took a vacuum, a tube, heated it up, curved it around in kind of this circular shape, and he, kind of melded on these ports here. This is for, working up to a vacuum port. This is an ion source. We'll talk about that, and that is the catcher foil up there. So here is the ion source, and what's going on here is very simple. I mean, this is a very, very, very primitive type of accelerator. And he has here a, this thing is hooked up to a power supply, minus high voltage power supply, like this. And here is a little sort of cathode with a slot in it. And you can actually see the slot right there. There's a little horizontal slit that's just a fraction of a millimeter wide. And this thing here, you can also see here, those are little heating elements connected to these wires here. So he actually heats this thing up to several hundred degrees. The uranium, you can actually get evaporates, and then some of the uranium actually becomes ionized. And so you have uranium ions here coming out, which are then accelerated through the slot to some tens of kilovolts. I don't know exactly what the voltage was, but you're a good physics student, you can calculate it looking at the dimensions here. Okay. So he makes a mixed beam of uranium-235 and 238, but all of them, independent of what the mass is, have the same common energy of Q times the voltage, which will be some tens of kilovolts, like that. Now, this thing is curved in a circle because what does he do? He puts it in a magnet. Charged particles in the magnet go in a circular orbit. And with a little bit of, since they all have the same energy, the momentum, p squared over 2m, is the kinetic energy. So the momentum is 2m. So for all the only thing you need to know is that this thing goes like the square root of the mass. So the momentum will depend on the mass, and the curvature of the field depends on the momentum. So what happens here is that you have this ion source. I'll draw it upside down. Where 235 would look like this. And 238 would go here. And if you just do a little bit of, if you say that's 40 centimeters across, you can actually calculate that the separation here, back of the envelope, you could actually calculate that it goes like the delta diameter over the diameter goes like 1/2 of delta m over m. So it's 3 out of 80. So it's like 1 part in 160. And you actually estimate, just looking at the size of that thing, I said it's probably 40 centimeters across, that this separation here, delta D, is just a few millimeters, 3 millimeters or so. So, moment of truth, they put the natural uranium in there, he runs it through the mass spec. That thing up there on the upper right is nothing more than a catcher foil. It's like a piece of aluminum foil, a little piece of few mil iron foil. They run this thing for several hours. They take it out, and he sees two discolorations, kind of two smears. One of them faint and one of them much stronger. The outboard one is, the larger radius is the 238. The inboard one is 235. He just sees a little discoloration on the foil. He takes the foil and he writes a letter.
This might be a stupid question.
Sure.
For I'm not an engineer, but if you're drawing, is that what's happening inside of
The tube, yes. Right, this thing gets stuck in here. He's just taking it apart. And the ions become here, but because they have slightly different momenta, they're.
Okay, so what's on the board is that flip?
Yes,
Okay.
exactly. I've got it upside down.
Okay.
And then up here is nothing more than a catcher foil. And that's it up there. It's a little piece, think of it like tin foil, except it's probably, I think that was a little piece of iron foil. And they run it and run it and run it. And after running it for a while, they actually see a little stain or a little discoloration. And he's got some few million atoms of this and a few thousand atoms of the other thing like that. And he then writes a letter to Dunning in Columbia, and he just tapes the foil to the letter and sends it by U.S. Post Office. And he makes sure the one on the left is the 238 and the one on the right is the 235. Don't screw it up. And the future of humanity hangs in the balance. So Dunning takes this thing, cuts it in two, puts it in the cyclotron. They run a deuterium beam into, some of you work with Lee Bernstein, you make a deuterium beam, you moderate it. They put this thing inside of a little fission counter, a little proportional chamber. They put the 238 in there, they run and run and run and see nothing. They put the 235 in there, turn the beam on, and there's signals galore. You see fission going on all the time. Imagine the chaos the world would be in had it been the other way around. I mean, every tiny little country in 1943 could have had a nuclear weapons program. Panama, Costa Rica, Lithuania. I mean, every country could have wreaked chaos on their neighbors if the fissionable stuff was the stuff you just took up from the earth, chemically separated, and you had weapons grade uranium-238. The world we wouldn't exist. The world would have been a total mess. Thank God, given that fission happens, that it was a minority component that takes a lot of work and a lot of expense to purify to make a bomb. One of my, Sir Dennis Wilkinson, very famous nuclear physicist, in his memoirs before he died, said, if I were God and had my way, I wouldn't have fission happen at all. But thank heavens that it was the minority component that was the fissionable one. But it was really interesting history. They just take this foil and he tapes it in there, and away you go. Interesting local history, and Michael, I don't know if you knew about this. There's the Lynn Seaboard. You can still, when you walk in the little alleyway with LeConte and Burge over here, and or Gilman Hall over there, you can see the room where Lawrence, built the first little cyclotron, the little Roland-Meyer flask, and then up the window up there on the second floor, you can see where he was actually doing the first separations, large-scale separations of plutonium in his office. Thank God it's a historical landmark, and they just basically walled off his lab with, lead shielding bricks, because otherwise it would cost them $200 million to remediate Gilman if you ever had to take the building down. So it's now a historical landmark, and we don't have to clean it up. Anyway, in 1941, we're not talking about plutonium, at the cyclotron in Berkeley, and at the cyclotron in Washington University in St. Louis, they start now doing major bombardments of uranium-238, making plutonium-239, and they begin to do chemical separations of this stuff. And they moved the whole operation to the Met Lab, it was called the G.J. Jones Metallurgical Lab at the University of Chicago. Seaborg, who is a premier chemist, got his friends, who were the premier chemists in the world, to join him on this project that they knew had an immense national security importance. And for months, all through the summer of 1942, invented whole cloth, the whole chemistry that allowed them to precipitate out this new chemical element that no one had ever played with before. Plutonium, I'm not a chemist, has fascinating chemistry to it. It's a very, very complex material. And they were able to separate out the first few micrograms of plutonium. From there, 2 years, 3 years down the line, they were now making, kilograms per month in these massive processes built up of both uranium and plutonium in, Hanford and Oak Ridge and so forth. Now, here's an interesting thing. In the summer of 2014, I was chairman at the time. I got a phone call from Phil Broughton, who was one of our EH&S technicians, who said, we got this cigar box over in the near the RFS, the Recreational Sports Facility, or the old first gym. He said they have this thing, which is the EH&S, the hazardous waste revetment. They store things in this kind of bunker-like things. If nobody wants it, mixed waste or radioactive waste, they ship it to a DOE site in Idaho and bury it. And he said, we're not sure what this is. There's some lore that this belonged to Glenn Seaborg, and it was the world's first plutonium. He said, do you want it before we ship it to Idaho and bury it? And I almost fell over. I said, is this a joke? And he says, no, come take a look at it. So it's a little cigar box, Alhambra cigar. And immediately I got goosebumps because apparently the Seaborg, everything that he stored in life was in an Alhambra cigar box. 5 cents. When was a cigar 5 cents? It was a long time ago. So anyway, I looked at this thing. There's a plastic bag, and there's this little lucite box with an eyepiece in it. And this eyepiece is a little platinum wire. And on the end of the platinum wire is a little shiny piece of metal about the size of a flake of pepper. That's it. And there was some typed, old-fashioned typewriter notes, asserted free from Seaborg, saying this was the world's first macroscopic source of plutonium that was separated in September of 1942. So we had a meeting of the faculty. We couldn't believe our eyes. And we said, should we take it apart? No, bad idea. Let's keep it in the box. It's plutonium. Should we do something at the ALS, the Advanced Light Source? Nah. And then one of the smartest guys in the department, Rick Norman, says, look, I have a Keenan Thomas, my lab tech, and I have a student from San Diego State University. We can do this just by passive gamma ray and X-ray counting, and we can tell you what it is. And so, okay, so they put up these gamma detectors and they measured the spectrum. They saw the lines, and they say basically this was consistent. The provenance of this was consistent with being 70-something-year-old plutonium. And their estimate for the weight based on the count rate was 2.3 plus or minus 0.4 micrograms. Said, holy cow, this is Seaborg's first plutonium. So we said, we're taking it, we will protect it, and so he wrote out a paper and it was accepted. I don't think it got into science, it got into some other journal. And what's interesting is that we contacted Public Affairs Office. What were we thinking? And said, this is really cool. This is like a moon rock. I mean, people, physicists look at this thing. This is like, holding in your hand the moon rocks that were brought back in 1969. Do you want to make a big splash on the webpage? And they said, are you kidding? They'll shut Berkeley down. It was a big story about Seaborg's plutonium. It was, lying around. Well, it wasn't lying around. It was all well protected. They said, no, thank you, but no, we're not going to do a big story. So anyway, he published the article. Next thing you know, in some obscure journal, everybody and his mother are calling us. And it ends up on blogs, it's ending up on Wired magazine and so forth. and it's getting lots of positive press. So the public affairs office said, "Oh, okay, let's do that story." So all of a sudden, that picture ended up on the webpage that week, and now we've talked with chemistry about they're building a little, kind of like a little museum room over in Town Hall, and it will probably be going there at the appropriate time. This was really exciting. We actually have now the world's first plutonium is not macroscopic. It's like that. It's a little bit of a stain on metal foil. That's in the Smithsonian, but it was in the Alhambra cigar box as well. Somebody in the Alhambra cigar box. But anyway, exciting. So here's what that Meitner and Frisch figured out correctly. Slow neutron comes in, it gives it enough excitation energy that this liquid drop becomes unstable and begins to pull apart. The Coulomb forces are very large. It snaps at the neck. The fission fragments become racketing away. But this whole process of forming the nucleus transforms a lot of that Coulombic potential energy into heat. So the two daughter nuclei are highly excited. You get some prompt neutrons. You can even get neutrons from the daughter nuclei. And then very quickly, you get lots of gamma rays. So we've talked about that before. I don't we revisit that. What's the budget sheet for fission? Total is about 200 MeV, which is very consistent with Lisa Meitner's estimate for what the Coulombic repulsion energy is for two touching nuclei, to transform that potential energy to kinetic energy at infinity here. 166 MeV on the average, the kinetic energy of fragments. Most of the energy is kinetic energy of fragments. You get out a couple of neutrons, 2 to 3 neutrons. From event to event, it changes from nucleus to nucleus, whether you're talking about the range 233, 239, 236, whatever, it will be a little bit different, but it's in the range of 2 to 3. About 14 MeV in gamma rays, either prompt or delayed. We talked before, we'll go this again, that you make things which are neutron rich. Once you form these things, then the daughter nuclei begin to now roll down the hill, so to speak. They begin to beta decay down towards the valley of stability. So you get 2, 3, 4, 5 beta decays, and so you get something on the average of 5 MeV in delayed betas, which can be milliseconds to seconds to minutes to hours to many, many years. And then neutrinos, which are not useful, but we'll come back to that later in the course, because some of my clever friends now have actually used neutrino detectors to monitor nuclear reactors at a distance, but that's a hard game. But 200 MeV. Okay, as we mentioned before, if you actually put a straight edge around there, you actually see that if I were to break, for example, the nucleus into 2 equal parts, you're way here on the neutron-rich side of the valley, and then a number of beta decays have to occur to get down to stability. For reasons that those of you who have taken 101 or 201 know, or at least are familiar with from a phenomenological point of view, strangely, nuclei do not split symmetrically. They tend to actually favor an asymmetric split with something around mass 130, something around mass 90. Go figure, but I mean, there's good nuclear structure reasons why this happens. And there tends to be a valley actually at symmetrical split if you look at the distribution of events there. Okay, what are the 2 isotopes in which one can most readily make a reactor or a weapon? 235. Under absorption of a neutron becomes 236, which then fissions immediately. Plutonium-239, under absorption of a neutron becomes a 240 and then fissions immediately. One, you just dredge out of the Earth, and you've got 4 different strategies, which we'll talk about later on. We'll actually really focus on the centrifuge, maybe electromagnetic separation, to separate out the 235 and get it up to 90%, a few percent if you want to make a reactor, 90+% if you want to make a bomb. 239 uranium you make by a byproduct, because if you're running a uranium reactor, most of the uranium is still going to be 238. It absorbs a neutron, it becomes 239, beta decays to neptunium, beta decays to plutonium, and then that's long lived, I think 12,000 years or so. Fission products, it's not the very short-lived ones, the very long-lived ones which are problematic, but the ones in between. Short-lived ones, well, you just wait a few hours and they're gone. If they're very long-lived, they never decay anyway. It's the ones in the middle that have some years or tens of years or hundreds of years of lifetime, which are problematic both from a waste disposal point of view and also a human hazard point of view. A few that you should worry about growing up in the 1960s, when we still did above ground, 50s and 60s above ground nuclear testing. We did all our testing after 1960 below ground. Everyone said, oh, strontium-90, it's in the atmosphere, it comes down, it's get absorbed by the earth, the cows eat the grass, we drink the milk, children have strontium in their teeth, you've got lots of problems, and in fact, that's probably true to some degree, but I think that most of us probably have not suffered ill effects from having strontium-90 in our teeth as children. Here is a much better example than I showed you before. Here is what's called the A chain. If I take a diagonal cut through the valley of stability, this one turns out to be a rather pretty parabola. The others look rather embarrassing. But here you can see on the parabola the energy differences. There's a correlation between the Q value, the energy to go from, for example, tin 119 to uranium, 137 europium to 137 samarium. The bars didn't turn out great. Yeah, let's look over here at the beta side here. You can actually see those bars. There, so you have 137 antimony, tin, iodine, xenon, cesium, and so forth. And you see you get this, chain of beta decays that goes from 450 milliseconds, 2.5 seconds, 25 seconds, 3.8 minutes, 30 years, and then you're down here. So you see this cesium-137 is a bad actor because it just lives inconveniently. You can't wait it out, but it lives long enough that it's going to be a problem from sort of a human health point of view. A couple of articles you want to see, and that's it. If there's not questions, I'll turn it over to Professor Knott. And I'll put this up on the web tonight. If anybody would like to see the plutonium, I think we can arrange some report.
There's a question.
Question.
How much would it cost to buy the first plutonium?
Wow, that's it. You mean, you would actually, I see, so you're a benefactor to Cal. We should talk. It would a lot of money, but I don't think it's something, interesting question, who really owns it? It may be a federal asset. How much are you willing to pay?
And I'm also wondering, so when the uranium oxide fissions, what happens to the oxygen? What does the oxygen do when the uranium splits?
Oh, it's just a spectator. If it's in a bomb in a critical assembly, it will also get pelted with neutrons and become something else. But it is just simply a bystander.
Did the discovery or anything of the cigar boxes, anything else cool? Did you chance say it was next to some other stuff from the lab?
Well, it's interesting. Some people said, well, the university is very responsible. Why was this thing just kicking around? Interestingly, it was up in display at the Lawrence Hall of Science, which is designed for 2 to 12-year-olds.
Sure.
And most of them, they want to go out and play on the dinosaur, the 70-foot whale in the plaza, or this and that. People, at some point, the curator, Lawrence Hall of Science belongs to the university, it's part of Berkeley, sort of said, you know what, this is not attracting a buzz. And by the way, plutonium, take it away. So it was in good keeping. nobody paid attention to it when it was up there, and then it went down into the EH&S, Environment, Health, and Safety people. Other than that, there was just take notes. Seaborg is an interesting guy. From the time he was a child, he kept a journal. Everything in his life was written down because he knew, he's one of these guys that knew that he was going to be a man of history. And therefore he recorded everything that happened in his life. And there are wonderful notes when he took the train ride from Berkeley to Chicago. He had a fiance at the time, and he was talking about communication with his fiance and his friends. We checked into such and such a motel. I met Moore and all these people there. That journal is in the Smithsonian, but to this day, the feds have blacked out certain things in his logbook because they are still classified. But there was this little eyepiece that they put it in this little plastic box. This must have been rather modern, such that you could look in there and actually see an enlarged version of this thing that was really like a pepper flake, and it was in a baggie, a Ziploc bag. I'll see if we can get a tour. You will not be able to rub your hands on it, but you can tell people that you saw this thing. Questions?
Okay, so this was a fascinating account of Fission from the late 30s into the 40s, and I just want to now resume the discussion about the thinking about nuclear weapons from the time the U.S. used the 2 bombs against Hiroshima and Nagasaki into the early 50s. Actually, there's something, a couple of points I mentioned from last time. I just want to go back to. I mentioned that there was the arrest of Julius and Ethel Rosenberg for espionage, providing information about U.S. bombs to the Russians. And David Greenglass, who was Ethel Rosenberg's sister, provide the critical testimony made a drawing of the Nagasaki bomb, the plutonium device, to Rosenberg, who gave it to the Russians. Because of his willing to turn state's evidence, he got a 10-year sentence, whereas his sister and her husband were given the death penalty. It's interesting because Greenglass only died in 2014. 2 years ago, he was 92 years old. Now, ironically, I was just looking at the New York Times the other day, and just last week, there was an obituary. I don't know if you happened to see it.
I actually sent it to.
Of Martin Sobel.
Mm-hmm.
Martin Sobel was a classmate of Julius Rosenberg at City College of New York. And he's a very smart guy, electrical engineer, and he was recruited to the bomb program in Los Alamos.
Mm-hmm.
And he also conveyed bomb designs to Julius Rosenberg, who communicated to the Russians. And he was given, Martin Sobel, S-O-B-E-L, a 30-year sentence. But it was commuted to about 18 years. And he died last Christmas, December 26th, 2018. And he was 101 years old. So there's some questions here about equity. But the whole controversy of the Rosenberg business continues to this day. Now, the bombs were dropped on those 2 cities, And today, the language that's used to explain that is a counter-value attack. We're going to get into the current terminology of nuclear weapon use next time. Counter-value versus counter-force. Counter-value are attacks against population centers. Counter-force are attacks against weapon systems. There's also something in between counter-urban industrial, which is manufacturing and other capabilities to build weapons. Now, from all the material that's available, the whole discussion about the Truman decision never considered anything other than primarily counter-value attacks. They were cities, they weren't the huge population centers like Tokyo or the very treasured religious centers like Kyoto, but there were cities where thousands of people would get killed, but they also were industrial centers. So one of the questions that arose right after the bomb in the United States was, should the bomb be essentially a counter-value weapon, or should it have other purposes? In 1946, and this is discussed in detail in the Kaplan book, a young political scientist, actually, named Bernard Brody, who had gotten his PhD at the University of Chicago and had written a book on naval strategy, who was actually very facile in absorbing technical information and military information, even though he wasn't a military man and not a technical guy. He joined a group at Yale University in New Haven at the Institute of International Studies. And Brody began to write and think in the most creative ways about the future uses of nuclear weapons after the atomic bombs were dropped. And he published a book, The Absolute Weapon, only a year after the bombing. This is an edited volume. But he had grave concerns whether there was any future use of these weapons, because the explosive power was so profound, the destructiveness was so terrific, that he went back and forth on this. Actually, it's another point in the 40s that Kaplan describes this. He talked about limited use of nuclear weapons, but he eventually came to the view that these weapons can never be used for military purposes. They can be used for coercion. They can, you can threaten to use them. You can use them to further political or diplomatic agendas, but not to actually kill people. That was his view, which was a new view, but also a minority view. In the actual material that's available about the Air Force, I mentioned that the National Security Act of 1947 created the Air Force, and the Air Force was in charge of the nuclear weapons, which were all delivered by bombers at the time. There wasn't a lot of creative thought about how to use these weapons. The thinking was about, if they tell us to use it, we'll use it. We just want to make sure we do what we're told to do. So the Air Force was not, this has changed a little bit over the years, the Air Force was not a kind of locus for creative thinking about nuclear weapon use. We don't really know the Soviet analog. This material still is not totally clear. But Brody was in the lead, and he had no clearances. He wasn't in the government. He wasn't a purely technical guy. He had no access to, he only had the newspapers. But he became the first so-called civilian strategist, and this book's actually called The Civilian Strategist. The nuclear weapons are so destructive that they allow people who don't know anything about military affairs or technical issues to weigh in. And he began to write articles. He wrote articles in a particularly popular magazine called The Reporter, which I remember subscribing to as a kid, 1,000 years later. I should say, I didn't know Brody was at this time, but I didn't get to know him later He went from Yale to Princeton. The president of Yale changed hands, and the new president of Yale decided that Yale had no business studying these issues. So he closed down the Institute for International Studies, and the key people from the Institute got an offer to go to Princeton. So Brody went from Yale to Princeton. Then he spent 15 years at the Rand Corporation, which I'll talk about in a minute. And then after that, he was at UCLA teaching international relations. By that time, that's where I met him. And there's a funny story. He was getting a little bit older at the time, and he was famous at UCLA because he used to teach an introductory course in international relations to 350 students, and he would frequently fall asleep in the middle of his own lecture. He was known on the campus. He had a very talented wife, Fawn Brody, F-A-W-N Brody, and they actually co-authored a book together. It's quite a prominent book. It's really worth reading. It's called From Crossbow to H-Bomb. It's the role of military technology in international affairs. And they go from the crossbow to modern weapons. It was published, I think, in the 60s or 70s. He wrote several major books. He was a beautiful writer. Everything he wrote was almost like poetry. It was beautifully written. This idea of Brody's in that volume initiated a debate within an academic community. It's not clear the government was playing much of a role about the utility of these weapons. Now, in the meantime, there was a separate internal debate, classified debate, and that was whether the U.S. should move from fission weapons to thermonuclear weapons. You know, if you've read it at all about it, Teller was interested in the thermonuclear weapons from the beginning. He was actually not that interested in fission weapons when he was in the Manhattan Project. It didn't play such a central role in the atomic bomb. And Oppenheimer left him alone so he could fiddle around with thermonuclear weapons. Later, after the war ended, Teller became a huge proponent of an H-bomb program for the United States, and he was very adept at gaining political support for it. The key figures at Los Alamos were not supportive of it, and Oppenheimer in particular was opposed to it. He said that the A-bomb is destructive enough. We don't need something that's 1,000 times more destructive than the A-bomb. Teller was able to gain support. It was not possible to overrule the leadership at Los Alamos, but Teller was able to gain support for the building of a second weapons laboratory. And that became Lawrence Livermore National Lab. Teller was not the first director of this lab. Herb York, I think, was. And actually, just recently, another major figure, Harold Brown, who was Secretary of Defense under Carter, and he was an early director of Lawrence Livermore. He just passed away. He was 91. I knew Brown as well, too. Hyper smart. He had graduated from high school, Bronx High School of Science in New York at age 15, and got his PhD in physics from Columbia, I think, at age 19. And he primarily worked inside on weapons his whole career. He was president of Caltech for a while. So you have these two parallel tracks, is what I'm trying to explain. You've got a public debate amongst some defense intellectuals about what the utility of these weapons are, and then internally, primarily in the scientific and military community, you have a debate about thermonuclear weapons. Lawrence Livermore Lab was not established until 1952. But before that happened, in 1949, much to the amazement of the American scientific community, the Soviets detonated their first device in 1949. There had been estimates. Truman had asked them for estimates of when the Soviets would get the bomb. They figured they were surely going to go for the bomb. remember the Truman administration did not know about the espionage program at Manhattan Project until 1950. And the estimate was between 1955 and 1960. So it'd be 10 and 15 years, they thought, before they could figure out all the intricacies of atomic bomb design and development and detonation. But yet it was only 4 years before the Soviets detonated. And this was a traumatic moment for the American scientific and military community. They were absolutely terrified how quickly the Soviets had latched on. This actually accelerated the intelligence community's efforts to find spies in Los Alamos. They figured, it was a guess, but they figured that it was unlikely that the Soviets could do this completely on their own without help. So 1949 was a crucial year that stimulated the decision by the United States to build thermonuclear weapons. Then in 1950, we have the beginnings of the espionage cases and the arrest of these key people. But also in 1950, a totally separate matter, but it was very influential on thinking, was in January 1950, the Secretary of State under Truman was Dean Acheson, a very prominent diplomat. And he gave a talk at the National Press Club in Washington, in which he was explaining what is the area of U.S. defense concerns and what area are outside U.S. defense concerns. And he mentioned specifically that Korea was outside the American defense perimeter. This was January 1950. This was a public speech. It was in the newspapers. It got to Korea right away. Korea had already been divided. Kim Il-sung had been selected by the Soviets to be the head of North Korea. South Korea was run by Syngman Rhee. And Kim Il-sung evidently requested to Stalin and to Mao, and also the Chinese Revolution had just been successful, so Mao was now the head of communist China, first time China had ever been unified. He requested their approval to attack South Korea. Kim Il-sung requested the approval of Stalin and Mao to attack South Korea, and they approved. So that was after the January speech by Acheson. And in June 1950, the North Koreans attacked South Korea. And it was a big surprise. The Americans were caught off guard. That South Korea was a very poor country with a very limited military capability. And Truman then reversed the policy. And he said, no, we can't tolerate this. This is aggression. And he wanted to go to the United Nations to get UN approval for military action. And there's a very special moment, the UN approval, I think you know, the UN Security Council has the 5 permanent members. They're the ones who vote, they have the veto power. Those 5 were the US, Britain, France, Soviet Union, and China, but the China seat was Taiwan, not the communists. So the Soviets had a veto power over this in 1950 after Truman asked the UN Security Council for approval. And ironically, and it's never been explained to my knowledge, the Soviet ambassador to the UN was absent for the key vote. So the Soviet vote was, I think, recorded as abstaining. It wasn't a veto, and therefore the vote was 4-0 to approve Truman's request for a UN so-called police action force to go into South Korea. By the way, another interesting feature of this experience is that according to US law, the Congress has to declare war. The president can request it, but Wilson requested the Congress to declare war in the First World War. Roosevelt asked the Congress to declare war in the Second World War. Now you have, it's going to be a big American military contingent going to Korea. Truman did not want to ask for declaration of war against North Korea. he was a little fearful that this could trigger a war with the Soviet Union. So it was called a police action. There was no formal congressional approval, and Truman authorized the deployment of US forces to Korea. This was a bitter, brutal, awful war. Korea has very hot summers, very cold winters. There was a whole other dimension to the war in that the Chinese, American forces had gone up near the Yalu River, which is where North Korea ends and China begins. The Chinese felt threatened by that, and the Chinese introduced forces into Korea. And there were actually more Americans killed by Chinese forces in the Korean War than there were Americans killed by North Koreans in the Korean War. This is the only key time when US and China have fought since Mao took over China. There were other moments, there were times when Truman was asked to consider use of nuclear weapons against North Korean forces. But in every instance, he rejected it, and he said, again, they're sort of flying blind. There's no literature, there's no agreed way of thinking about this. There's sort of, Truman said, no, atomic bombs must only be used to defend the continental United States. If the US itself was threatened, the US is not being threatened in this instance. You should not use atomic bombs in a regional conflict. This was a presidential decision, presidential, but also precedential. It set the precedent for future cautionary consideration of use of nuclear weapons. Yes?
So for that initial speech where they're admitting that they have no reach to Korea, that's what, I'm guessing it just.
Why did Atchison say that Korea was outside the defense perimeter?
Yeah, it just reminds me way too much of the May incident where they revealed the depth of US submarines versus the depth charges.
Yeah. I mean, they just, America had, in the 5 years since the end of the Second World War, the US had largely decommissioned its forces. We pulled out we had 12 million men in Europe. We pulled out almost all the forces from Europe. Americans have what I like to call, I'm a former engineer, an engineer's mentality, which is you have a problem, you've got tools, take out the right tools to solve the problem, and you forget about it, because anytime in the future you know how to solve that problem. But international relations is less of a problem, it's more conditioned. It keeps going on. The Middle East is a condition. Syria, ISIS is a condition. It's not like end of story. It doesn't normally end that way. So Truman was very reluctant to spend a lot of money on the military. He had already had problems with the Soviets, and they had detonated the bomb. But he wasn't calling for a huge US military buildup. And they would just, say, we've got to set limits somewhere. Korea's sort of on the other side of the moon. Forget about it. Remember, this is very kind of crude and elementary thinking about things. They don't know what's coming. Now, another key element around this time is the Air Force was aware of Brody's writings and aware that they really weren't doing creative thinking about use of nuclear weapons. So Donald Douglas, who was the head of Douglas Aircraft in Southern California, met with some key Air Force personnel and said, we need to establish, and I think they were one among the first to use the term think tank. Think about, just have people think, which itself was a kind of crazy life. You're just gonna have people think. Like, my father was a small businessman when I first got into academia. He said, I understand what you do. You go into an office, you put your feet up on the desk, read magazines, and they pay you. That's it? So I said, yeah, that's sort of it. So this was really the first think tank that was established after the war, certainly in the national security area. It was called Research and Development, and it purposely had an innocuous name. What it was doing was the most sensitive classified thinking about U.S. nuclear weapon use. And it was established in Santa Monica, California, not far from Douglas Aircraft. And it still has a major complex in Santa Monica. They refurbished it. They also have an office in Washington, across from the Pentagon, in Pentagon City, if you know where that is, in Alexandria, Virginia, I think, or Arlington, Crystal City. And then there's also, they've opened up some other offices in Pittsburgh and in Belgium and a few other places, because they've branched out into non-military work. So, then the RAND Corporation remains a very vibrant, vital organization to this day. There's all kinds of interesting research work. In the early 50s, RAND took on a major study, which turned out to be very important. You know, we had these weapons, we were accumulating new weapons, but the Soviets had weapons. So simple question, you know, where do we put our weapons? Where do we put them? So the decision by the Air Force was, let's put them on the coast, on the West Coast and on the East Coast, so that if there was an attack, they could get off the ground quickly and get in the air toward the Soviet Union. We were going to retaliate before they were destroyed. RAND was asked to rethink this strategy, and it became known as the RAND Basing Study. This is a highly classified study, producing a report in 1953. The first major article that was published about the study came out in the late 1950s by the team leader of the project, Albert Wohlstetter, O-H-L-S-T-E-T-T-E-R. He's an amazing, difficult character who I tangled with personally later in his life and early in my life. I'll tell you the story in there's a minute. Wohlstetter claimed, and his team claimed, that the nuclear balance between the US and the Soviet Union was not stable. It was thought, you know, they have a lot of weapons that can kill people, we have a lot of weapons that can kill people, nobody's going to use the weapons. Wohlstetter said, no, if the nuclear weapons of one side are vulnerable to attack, and the attacking side thinks they can destroy most of these weapons, then they would have an incentive to strike first. So this would be a counter-force attack, not a counter-value attack. He said what's essential is, and this was a key finding of the study, to develop an invulnerable second strike capability. That no matter what the Soviets did, the US had sufficient resources left to inflict tremendous damage on the Soviet Union. And that would be enough to dissuade the Soviets from attacking. The article that was published in Foreign Affairs in 1959 was called The Delicate Balance of Terror, claiming that this was a non-trivial situation. And that article is described in Kaplan and the importance of its thinking and affecting Air Force thinking. So what did that mean? It meant that the nuclear weapons should be based in the hinterland of the United States, in Montana, in Missouri, in Wyoming, not on the coast. You don't want to make it easier to be attacked. You want to make it difficult. You want the Soviets to have to destroy a lot of America to destroy these weapons. So, to summarize on these bullet points below, The arguments of the thermonuclear weapons were stimulated by the Soviet first nuclear test, by Soviet espionage of the Manhattan Project, and by the Korean War. And that's about as far as American thinking got about nuclear weapons. It still wasn't very well developed. Truman decided not to run for re-election in 1952, and Eisenhower became the president. I was a military man, commander-in-chief of the armed forces in the European theater, the whole architect of the D-Day invasion, a major national hero. But he didn't want to spend a lot of money on defense either. And he thought, you know, nuclear weapons might be a cheap way out. You can use nuclear weapons to threaten folks, and we won't use a lot of these weapons, we won't need them. So he asked his Secretary of State, Dulles, John Foster Dulles, who's a known anti-Soviet hawk, to come up with a label which today we would call declaratory policy. What is the U.S. policy on nuclear weapon use? And Dulles wrote an article that also appeared in Foreign Affairs in 1953, where he coined the term massive retaliation. And in that article, he basically stipulated that this was a direct threat to the Soviet Union by the United States. If the Soviets even engaged in limited military action, supposing they brought forces into Southeast Asia somewhere, that the US might attack Moscow with nuclear weapons. The publication of that article triggered a huge debate, bridging now the military technical people with the civilian strategists. Brody got involved in the debate. A young assistant professor at Harvard named Henry Kissinger got involved in the debate. A man named William Kaufman, who wrote a key piece on the requirements for deterrence while at Princeton, got in the debate. And what evolved over the late 50s was the judgment that massive retaliation was not a credible policy. What did we mean by that? The critics meant that, and we'll go into this in deterrence in just a minute on the next page. Missile is misspelled there, sorry. Yes?
Just curious, did any of these committees, either the Gator Committee or RAND, discuss kind of the ownership of nuclear, like the authorization to use nuclear weapons? Because I know between Truman, Eisenhower, and future presidents, there's a whole discussion about whether there's checks on the president to use it versus military being more responsible to use it.
Yeah, no, it was decided very early on in 1946, just a few months after the Nagasaki and Hiroshima bombs, that the president himself, the civilian leader of the armed forces, would be the only one who could authorize nuclear weapon use. It could not be authorized by any military officer. The military resisted this, but Truman prevailed. And that has been true to this day. So today, it's Donald J. Trump.
I thought there are specific, there are conditions in which the president doesn't have to be in the chamber, right? Didn't command and control establish specific?
Not on nuclear weapon use. On nuclear weapon use, it's supposed to be the president himself has to authorize first use of nuclear weapons.
Are other people or other groups able to oppose that?
Not opposed, they can chime in,
But they can't.
they can't overrule it. Now you get into, we're going to go into later on tactical nuclear weapons used in the region and so forth. But even there, we had 7,000 nuclear weapons in Europe during the Cold War. And those weapons could only be authorized by the United States and by the president. You have doubts. You have doubts.
I mean, so when you say for launch, I mean, this is for retaliation.
No, For, it could be first use. Any use of US nuclear weapons comes from the President of the United States in conjunction with the Secretary of Defense. He's the other person in the, you're saying no.
No, I thought they introduced something that would stop that, because one, if that means that there's a choke point at the top.
Nuclear weapon authorization to anyone other than the president. You can look it up. If you find something different, I'm happy to discuss it. Okay. So the argument from the mid-50s on was a critique of the Dulles massive retaliation strategy. But there hadn't been any replacement strategy yet. This didn't come in until McNamara became Secretary of Defense in 1961. And I think I'll wait and discuss that next time. So what I do want to mention about the Gaither Committee report, that was in the reading assignment. The Gaither report, Gaither was the chairman of the board of the Ford Foundation, and he was commissioned to head a group to review what we knew about Soviet military forces and what we should do about it. And they concluded in a classified report that went to Eisenhower. Eisenhower was reelected for a second term in 1956. The Gaither report came out in 1957. The Gaither report asserted that there was a huge missile gap between the Soviets and the United States. That the US was in fact now behind the Soviet Union. I won't repeat that. So, as the 50s are winding on, we have a questionable declaratory policy, massive retaliation, that hasn't been replaced by anything. We have an intelligence failure of a missile gap that didn't exist. And we're still kind of trying to understand how to use these weapons. Okay. What does become apparent, and especially starting in the 1960s, is that deterrence is the key concept. And deterrence is a term used often, but not used carefully. So I would like to just quickly summarize the conditions of what deterrence means, and then give you a kind of crazy example. I'm asserting for you now, and this is not in the book, that suppose you have two sides, could be two countries, could be a man and a wife, could be a labor union and management, it could be two competitive organizations, A and B. And I'm asserting that A deters B if each of the following conditions are met. First, A threatens B, that if B carries out a certain action X, A will punish B. It's an if-then threat. If you do this, we do that. It has to be the case that B receives the threat, B hears the threat, or learns of the threat. This might seem trivial, but it's not trivial in international politics, because international politics is very noisy. And oftentimes the government doesn't hear the threat. I'll give you an example. During the Vietnam War, Lyndon Johnson said many, many times on television and in the newspapers that he's going to bomb the North Vietnamese to the conference table. He's going to keep bombing them until they negotiate. Later on, many years after the Vietnam War ended, a group of Americans went to visit Hanoi, and they said to the North Korean leadership, North Vietnamese leadership, including General Giap, and I don't know if Ho Chi Minh was still alive, he might have been. He said, well, what did you think of the Johnson threat? We're going to bomb you to the conference table. They said, what threat? They never heard the threat. So it's not necessarily the case that every time you threaten, the other side will hear. You've got to sort of make sure that that's the case. B receives the threat. Then B has to calculate, this is the recipient of the threat, that A has the will and capability to carry out the threat. This is very subjective. You don't have a meter that assesses this, right? Will and capability. And will plus capability equals credibility. That's the credibility of the deterrent. So, for example, Americans convinced themselves that the Russians went into Burma, we would not have the will to bomb Moscow. We just wouldn't do it. Why? Because the response is totally disproportionate to the action being taken. So then B has to do a cost-benefit calculation. B has to determine that the punishment it's going to receive from A outweighs the gain of taking action X. And if it does, and B decides not to take action X, then B is deterred. Now, any questions about that? It's a little abstract. Let me give you an example, crazy example. Okay, here's my example. Years and years ago, I had a son. I still have him. His name is David. He was 8 years old. He's not 8 years old today. He's much older than you guys. Okay? And now this rest is hypothetical. David is having trouble in school. So his mother and I agreed to tell David, you cannot turn on the television unless you do your homework first. Okay? And David knows that. We've told him that. He hears. He understands. He's in elementary school, but he understands. I come home from work early one day, and I go, years ago they had there was a television in the so-called family room. Right? This is before you had time. Like a room that might have some books and sofas and a television. And by the way, this was before the age of remote control TVs. You had to physically go up to the television and pull a button and turn it on. I know this is hard to believe, but it really is true. So I get home early from work and I go into the family room, and there is my son David walking toward the television. And it's only like 3:30 in the afternoon. And I think there's no possible way he could have completed his homework by this time. So I say to David, David, if you turn on the television, I'll break your arm. Now, what's happening here?
You
Yes.
have to evaluate whether or not prior experiences with you determine that you have the credibility to actually break his arm if he turns on the TV.
Exactly.
Well, he has to evaluate first whether or not, he's actually breaking the rule, because he could have done the homework and you don't know. Your threat was, if you turn on the television and have not done your homework, I will break your arm.
Right.
More likely
But I didn't say that.
that.
I'm assuming he hasn't done his homework.
So regardless.
And let me ask you this, do I know for certain that he was going to turn the television on?
No.
He's walking toward the TV. Do I know with 100% certainty? No. So there's already some uncertainty going on here. But let's assume he hears my threat. Now, if he's 8 and I'm a little older, does he think I have the capability to break his arm? Probably he does. Today, he'd break my arm, but then he probably thinks I could break his arm. Does David think I have the will, that was your point, to break his arm over the turning on the TV? How many of you think that David would be convinced I would have the will to break his arm?
That would be subjective, I would say.
Yeah.
Based on prior experience.
If you're
You've broken his arm.
Under the belt.
I mean, if you're the same guy to give a threat like that, I assume you
No, I've never broken his arm before. How many of you think that David would not believe that I would break his arm? How many of you think I would not? How many of you think David would not believe? Not believe. Some of you. How many of you think David would believe I would break his arm?
Only because of the mind of the child.
Only because of what?
Only because of the mind of the child. If you were a
I
more
see.
mature adult,
Okay.
with an adult thinking process.
Let me flip it around. Supposing instead of David, there's a guy climbing through the window. It looks like he's going to try to steal the TV. And I say, you steal that TV, I'll break your arm. How many of you think that the robber would think I would at least try to break his arm? Is there anybody here who doesn't think I would try to? What's the difference between the two situations?
There is a certain experience of your child. He knows whether you would like to break his arm. He probably knows that you love him, and probably this threat is just to avoid the conflict once he turns his TV on. But with the robber, the situation is different. You don't know each other, so the robber probably will know for sure that you might hurt him, and so that's why he will.
Okay, I see we're over time. Let me get, the key thing is proportionality. Proportionality. My threat to break his arm is disproportionate to the action I'm trying to deter. Did you get that? Just have to have a proportionate response. I think I don't want to rush through this. There's more to this. I'll come back to it next time, and then we'll talk about containment as well. Okay?
I wonder if you have to do class after.